Dear audience, welcome to our session on our Ensenso 3D cameras. If you wonder why we cover 3D vision in our portfolio, you can have a look at our previous vision channel feature on 3D in machine vision. There I explain a few of the technologies that are used in 3D machine vision from the past and present. And you also get an overview of different current technologies, such as stereo vision realized in current products. Today's feature is about our Ensenso camera lineup. So I will go through our Ensenso product portfolio and tell you what the cameras from compact to high-end do for our industrial applications. Let's have a look at what we have. We have a compact Ensenso series called the N series, compact and robust with the active stereo principle. We have the X series in the center, a flexible and very powerful setup working with the same principle. Latest introduction to the Ensenso product portfolio was the XR series that has the same flexibility and power as the X series, but adds an SoC for embedded computation. I will first go through the N series. As I mentioned, compact and robust industrial 3D cameras. We have three families of active stereo cameras here, N30, N35 and N45. They all share a 100mm stereo baseline and 1.3 megapixel resolution sensors. You can have them with blue or infrared projection plus front light for calibration projects. The stereo processing works on your host PC for these compact cameras, but you can cover dynamic or static scenes with variants of these models. In total, for the N30 series, we offer 20 optical configurations that can cover from about 300 to about 3000 millimeter of distance. To give you a vague impression, the noise level that you get on a Euro palette is about 2 millimeters. New addition to the series is again a compact version, the N45, introduced end of last year. It's a new lightweight and cost-optimized version of this technology, and here we offer in total 8 optical configurations. Where are these compact industrial cameras used? Well, main principle, they are used for stationary setups or also for robot arm mounting. This is visualized here, the two different setups. At the bottom you see a robot arm mounted setup for inspecting wood, and on the top you see a stationary setup, in this case for bin picking. Moving to the powerful and flexible Ensenso X series. Here you can see that this is a bit larger construction of the same principle. We offer a 200 or 400 millimeter baseline in this setup. We have a 1.6 or 5 megapixel resolution. We still do PC-based stereo matching with the Ensenso X, and they also can cover dynamic or static scenes. In this case, the power of the Ensenso X means we can cover more ground, so from approximately 300 to about 5000 millimeters of distance. And to again give you an impression of the noise level you can achieve, here we reach sub-millimeter noise levels when we cover a Euro palette. Typical setups for such powerful cameras are shown here. So on top you can see a handling of large motor blocks, where you can spot the Ensenso X series below the ceiling, and same on the background image here, where handling of a very large pallet by a very large robot is shown here. In this case, the accuracy received here for the position of the individual packets is in the millimeter range. And the XR series, as I mentioned, taking the X series to the next level by adding embedded performance. So the XR series is also active stereo camera, but here we have an integrated onboard SoC for point cloud generation. This serves to reduce the PC host load. Again, this is available in two baselines, 200 and 400 millimeter, 1.2 kind of resolutions, 1.6 and 5 megapixel. It can cover dynamic and static scenes. And as for the X series, we can deliver it in a user-defined optical configuration, or you can even calibrate it in field to your defined optical configuration. Where would you want to use the XR series? Well, the host PC offloading works best for multi-camera setups. So scenarios like this, where you want to cover a large object, potentially also in motion and with several field of views at the same time. So here it's a large example drawing. And here are some images from a research project where prototypes of the XR series were developed and used to cover a slow-moving production line and to give some information to compare the current components that are assembled with the model components from the database to figure out if everything is assembled correctly or some wrong configuration or wrong component has been used. This was a short introduction of the three series. Now I want to dive a little bit into the technology. So the goal here is now that you understand what the active stereo vision principle is that is used in all the Ensenso series. So the 3D imaging technology is based on stereo. That means we have two cameras. They acquire two images from slightly different perspectives determined by the baseline. And with this setup, like humans and mammals, we can determine distances by doing triangulation. So the triangles that you see in this sketch can be used mathematically to determine the distance to the individual objects or cones shown here. The computational challenge is here to find corresponding pixels or areas in the images. So looking at raw images might look like this. You want to find the tip of the cone in the background. So you have to find the corresponding pixel in left and right hand image here. And in order to do that efficiently, there's an important step that you want to do with the images that is shown here. So from top to bottom is first getting rid of the distortion. So those black lines become straight lines, and then also rectifying the image pair. So that means I have only to search for corresponding pixels in the same image rows. This is of course more effective than searching in the full corresponding right-hand image. So once this is achieved, then algorithms can get to work to find matches, and this will end up in for example, these two values here. So we see here one example where the offset between left and right image is 25 pixels. And we have one more example where the offset between left and right image is 50 pixels. This offset is called disparity. And this disparity value can be translated into a distance. And so on top, you can see here a disparity map that shows the different distances that can be seen in this image. And having this distance information, we can now create a point cloud. So that means assembling X and Y coordinates from the pixel positions with the distance as Z coordinate, and then we can render it here. In this case, a gray value representation of the texture added here. So this is stereo vision in machine vision in a nutshell. However, I mentioned that Ensenso use active stereo vision. So why do we do that? Well, if we look at industrial setups, they can be very homogeneous. So think of metal surfaces, white walls, and so on. Here we have foreground and background, which is quite homogeneous. And the red bar here shows you that in this case, it's very difficult to find its corresponding pixels. So we have homogeneous scenes. We want to have more texture in the scenes, because if we match like this, then the algorithms will basically give us limited set information. So that's shown here. All the colored points means there is a distance, but there is a lot of distances missing in the scene. If we add texture by using the projector of the Ensenso cameras, then the raw images become like this. And you can see here that with this texture, basically all the scene areas can be matched. And that gives us a very filled distance map or disparity map, very filled point cloud data. There is one more thing. Because of the different perspectives of the camera determined by the baseline, we have, of course, shadowed areas. So now I've introduced the projection. Let's look what the Ensenso do in that projection. So looking at dynamic or static scenes makes a difference in how you can use the projection. For dynamic scenes, you always want to make single shot acquisitions. That means you take one stereo image pair and project a static pattern into it. And in this case, the Ensenso use this random pattern, a filled random pattern for dynamic scenes. This is realized in the N30, X30 and XR30 models. When you have static scenes, then you can do a bit more, let's say, sophisticated projection. That means you can change the projection over time. And this is realized in the so-called FlexView technology that is integrated in the other Ensenso models. Shown here are the two patterns used with FlexView. So in the center, we find the pattern used in the N series for static scenes that is identical to the left one. And on the right-hand side, we find the pattern used in the X and XR series that has a difference in that there are vertical stripes, meaning horizontal gray value variations in there to optimize the matching. So what does FlexView mean? Well, as I said, we can change the pattern over time. And in this case, what we do is we just shift the pattern and take exposure sequences. So when I want to look at that, here's an animation of raw images where you can see the FlexView sequence. In this case, it's a right-hand image of a car tire, and you can see how the pattern is shifted across the object. And taking all these images together allows to get higher accuracy in the data. So now we have the image acquisition and projection. Let's look at how we can operate in terms of algorithms. The Ensenso flexibility finds itself here that we have optimized options for performance or for coverage or data quality. Today's choice of the stereo matches that can be used in the Ensenso cameras are three. First of all, the original one is the semi-global matcher. Let it suffice to say here that it's a very fast algorithm, efficient for dynamic scenes. The static scenes is here in brackets because there are other algorithms that are optimized for static scenes that perform in generally better here. But still, the semi-global matcher is a very flexible option. Next option is the sequence correlator. Here you can see in the sketch here that it takes several images. It produces in general very high quality data for static scenes. And the newest option introduced last year is patch match. That's a very flexible, innovative algorithm that works for both dynamics or static scenes. And it brings with it an infinite distance range in the matching process. So you might think, why infinite distance range? What's the interesting thing here? Well, I have put in a few more pictures to show to you where this could be interesting. So here is a setup or a scene that from our lab, and in this case it's a raw image without projection. You can see that we have foreground and background objects. We have a firewall in the background, and just on the bottom side we have a carton box, so to speak, in the way of the field of view here. So let's look first at sequence correlation. So if you put up sequence correlation and take a certain, let's say, compromise between data quality and coverage, you can end up with a point cloud or coverage like this here. You see that the coverage starts in front of the Euro palette and extends back to the about 5 meters far wall distance. And in this case, that means our coverage will basically cover about 2.5 meters in distance. Now, if I switch to patch match, the infinite distance range means that patch match is also able to get the very foreground, so the carton box in the way, or even the table on the left-hand side. So this is very interesting if you need to look for obstacles that might be closer than your actual usual working volume. I'll show you another perspective on this using the rendering in the Ensenso SDK. So here you can see the setup again with the sequence correlator. The distance from camera to the Europalette is about 2.5 meters. And here you can see the volume covered by sequence correlation. And changing to patch match again shows that we can cover more ground. We can cover the foreground as well. So this is the innovation in the patch match algorithms. Now I've flown over all the options that you have in hardware and software. How do you now choose the Ensenso model for your application? The first step would be to go to our IDS website and go to our Ensenso camera selector. The idea that you can bring to that is what kind of working volume you want to have covered. So the XYZ ranges you need to cover, and also the distance to the working volume. And you can enter these, and then it will spit out cameras that can be used for one or the other working volume and distances. Of course, there are great variances in what we can do here for close-by objects looking into small bins, and here again another extreme, looking from very, very far away at large pallets will give you different results. You can always then look at the result specs because the Ensenso selector gives you detailed data over distance range, in this case the Z accuracy and pixel size and so on. So here you can basically decide down on the exact configuration that would work best for you. Then one more slide on industrial robustness. So all the Ensenso cameras provide industry-grade housing. In the N series, we have compact housing with IP65-67 protection class. The N45 is our new option, more cost-efficient by providing a plastic-based housing, but with the same protection class. The N series can be used via power over Ethernet, so that saves power cabling. The X series offers two protection class. So one is also IP65-67 for rough environments directly. We also provide an IP30 variant for relatively, let's say, safe operations, or so what many customers do is provide their own housing or construct their own specific housing for applications using the IP30 variant only. The XR comes again with IP65-67, and all the cameras come with GIG data interfaces, push-pull or M12X connectors, and of course industrial IOs for trigger and flash to be integrated in systems with trigger or with additional cameras. One particular interesting point that comes from our LED-based projection in these cameras is that all the models are sorted into the no-risk group in terms of eye safety, with the slight exemption that if you look from very close distance into the projector of the powerful X or XR series, then you have a high illumination for your eye. But as I've shown you in the typical setups, you are usually far away from the camera. Now, integration on the software part means you use the Ensenso SDK, and here I want to go over the options or the components that we offer in the Ensenso SDK. Currently we have the Ensenso SDK 3.0, and this SDK supports all the Ensenso cameras I've mentioned. We have setups for Windows, Linux, and ARM-based Linux, like example for the Jetson boards. We have CPU and GPU processing options, including multi-threading. There are APIs in C, C++, and .NET language that you can use for programming the cameras. And there are interfaces to third-party products, namely Halcon, the robot operating system, and there is a new Python interface that you can use for rapid prototyping. Going over a few of the Ensenso SDK features, I would cover the calibration wizard and the calibration functions included here. So you can either use a simple 2D calibration plate available as accessory shown here, or you can use more complex calibration objects like put together many patterns on a dice shape here. And the features that you can use here are the in-field calibration. You can do a workspace reference. You can do hand-eye calibration with robotics. And of course, multi-camera setups that I've mentioned already. Software side, this looks, for example, like shown in the graph on the right-hand side here, that you put together information from color cameras, from 3D cameras into a tree structure. And having the system calibrated means you get one data set that is matched in coordinates out of that. The 3D plus 2D combinations are very interesting. We'll see a few examples later on, as you can freely choose from Ensenso and our UI cameras to find the combination that fits best for the application. More options, more features in the SDK include rendering, texturing, and also primitive fitting. Here comes animation that shows the rendering capabilities in the Ensenso SDK. So this is a smaller setup of a box with cartons inside, and you can see the texture that is produced by the Ensenso cameras and is used here in the rendering in the SDK to show, in this case, the boxes with etiquettes, and you can see that you could use this data now also to read, for example, the barcodes or the 2D codes in this scene. Going back to the overview of the features, there are two more I want to mention. So we have a remote access feasibilities for housekeeping, debugging, and parametrization also of the cameras. And we have file cameras and virtual cameras that are software constructs that can be used for debugging and simulation. So entering the final part here is, why is the Ensenso used? What do we do with them? So I want to point out that the Ensenso offer great flexibility. I want to cover research projects foremost. So, for example, in 2016, the winner team for the Amazon bin picking challenge used a combination of Ensenso N series plus color to tackle this kind of very advanced but logistics challenge in picking together typical from a typical warehouse with mixed goods and so on. Other projects look more at technology demonstration, in this case an intelligent robot that can collaborate and can play with humans. In this case it was a Scrabble against the US Scrabble master. And a third example here from a research lab in automotive production. That is a collaborative robot, and you can see here that these projects can be quite daring, trusting the robot to safely put your arms around a human. And you can also see here that the Ensenso N series can be used as the eyes for such new and innovative projects for research and development. Let's move on to industrial setups. It would be too much for this session to go over all the examples that I could show you. Let me pick a few for you. So one I pick would be trimming of foam parts. Here the Ensenso N series is used on a robot arm to get accurate data from multiple perspectives of seat cushion element, and this data is then used to mill this cushion element to perfect shape. As it says here below, the system is accurate to about 0.2 of a millimeter. And in this case, it was automating a process that was done manually before, and now it can run around the clock. Second example here would be the automatic 3D recognition of wood beams in order to print, to label them correctly. You can see on the upper right hand side the labels put on the wood, and you can see in the center the Ensenso mounted to a robot arm, and on the bottom basically the label positions are derived from 3D data and are here painted into the 2D image from the Ensenso, where the labels can be placed. So this is also an example for automating a previously manual, a process that was done manual before by using a robot with a arm-mounted Ensenso camera. Looking at only a few more examples, I would show you this again, very large palette for fully automated depalletising, developed together with ABB and in Thailand set up. And here very nice feedback from this customer that the Ensenso overall provides easy configuration, good SDK with stable API and flexibility. Last example I would show here is picking the unknown company. Our partner company Pfizer here is using the Ensenso with color combination to basically tackle new approaches for unloading here lorries. You want to come from also when the situation is shaded, so you are in a shadow area, you want to come to the situation where you can identify the boxes and then have them automatically unloaded. More of these application examples and specifics for these applications will come online in the IDS Vision channel. We plan more features on these, but also you can have a look at our case studies webpage, where there's a longer, ever-growing list of such nice of the breadth of the applications that can be solved with the Ensenso. And with this, I want to thank you for your attention and open for questions.